Okay, let's dive right into one of the coolest mysteries of the modern internet. Seriously, have you ever actually stopped to wonder how a brand new smartphone you literally just unboxed can flawlessly talk to some dusty database server sitting in a rack that was built a decade ago? It's kind of wild, right? Without a universal set of rules, every single manufacturer would just invent their own communication formats. A laptop from company A would be completely deaf to a server from company B. The real magic of the internet is that it runs entirely on open standards.
Welcome to This Explainer, where we're going to break down this invisible rulebook that makes your entire connected world possible. We're going to explore how any device, no matter who built it or when, can just join the global conversation simply by following these agreed-upon rules, which we call protocols.
So here's our roadmap for today. 1. Addressing the global network. 2. Delivering data. 3. The internet's phone book. 4. The language of the web. And finally, number 5. Seeing the whole protocol stack in action. Let's get into it. Kicking things off with Section 1. Addressing the global network. Focusing on the Internet Protocol, or IP. Let's start with the absolute foundation of all internet communication. An IP address is brilliant because it solves the two biggest problems of a network at the exact same time. It acts as both a name tag, asking, "Hey, which device is this?" and a GPS coordinate, asking, "Where exactly is it on the network?" Whether you're dealing with an older 32-bit IPv4 address, the ones written out with dots, or a newer 128-bit IPv6 address separated by colons, this foundational numerical label is what defines the routing rules for getting packets from a source to a destination. And this perfectly illustrates the original 1981 vision of IP, penned by the legendary John Postal. Just look at the language he used here. It was designed for an interconnected system of networks, what they called a catnet back then. The entire goal was to create this ultimate internetworking layer that could connect completely different packet networks into one unified address space. It provides best effort delivery of data blocks, and it even handles chopping up or fragmenting those blocks if they have to squeeze through a smaller network. But 1981 was a long time ago. The original IPv4 system gave us roughly 4.3 billion addresses. Now that sounded like an infinity back then, but we actually ran out of unassigned blocks in 2011. Crazy, right? So the solution was the transition to IPv6, which unlocks this absolutely massive 128-bit number. That equates to 340 undecillion addresses. To put that into perspective, that is literally enough to assign a unique IP address to every single grain of sand on planet Earth, with plenty of addresses left over. All right, moving on to Section 2, delivering data, the ultimate showdown between TCP and UDP. Now that we know how to find each other on the network using IP, how do we actually move the data around? Remember how I mentioned IP provides best effort delivery? Well, best effort means it doesn't actually guarantee your packets arrive or that they arrive in the right order. That is where TCP steps in. If you're downloading a file, loading up a web page, or querying a database, you absolutely need TCP. It's a transport layer protocol that ensures every single piece of data arrives perfectly in order. It numbers every byte, demands the receiver send back acknowledgments, and it'll automatically retransmit any lost data segments. The really crucial thing to understand here is that TCP was heavily influenced by its origins. Look at this excerpt from RFC 793. It was designed primarily around military computer communication requirements. It had to be tough. It was specifically built to survive hostile, unreliable network conditions and heavy congestion without ever dropping the ball and losing data. TCP basically assumes the network below it might be an absolute mess, so it takes on all the heavy lifting to ensure a reliable end-to-end connection. So, how does it actually do this? It builds a logical connection through what's famously known as the three-way handshake. Before a single drop of your application data can flow, TCP meticulously negotiates things. Step 1. The client sends a SYN, or synchronized segment, with a random sequence number. Step 2. The server replies with a SYNAC, acknowledging the client's number and announcing its own. And finally, Step 3. The client sends an ACK back to acknowledge the server. Only after this rigorous three-step dance is the connection officially open for business. But what if you simply don't have the time for a meticulous three-step handshake? Enter UDP. Unlike TCP, UDP is built for sheer speed. It gives you connectionless, unreliable delivery. No handshakes, no acknowledgments, no retransmissions. Now, you might be thinking, why would we ever want that? Well, in latency-sensitive applications, think video conferencing or online gaming, a packet that arrives 200 milliseconds late is actually worse than useless. By the time it gets there, the conversation has already moved on.
As this snippet from 1980 confirms, UDP was intentionally designed to be incredibly bare bones. It's described as having a minimum of protocol mechanism. It is basically just a thin wrapper around IP. In fact, the header for UDP is only 8 bytes compared to TCP's bulky 20-plus bytes. It just gives you port-based addressing so different apps on your device know where to receive data, but it leaves any error handling entirely up to the application itself. It's DIY error correction. So it's vital to remember that TCP and UDP aren't really competitors fighting for dominance. They're complementary tools in the protocol suite. You're going to choose TCP when every single byte matters and timing is a bit more flexible. But you'll choose UDP when blazing fast speed matters above all else, and sacrificing a bit of perfection, like, say, dropping a single frame of your video stream, is totally acceptable.
Moving right along to Section 3, DNS, the Internet's phone book, and how we translate human names.
So how do we humans actually navigate this purely numeric world of IP addresses? I mean, human brains are pretty terrible at remembering random strings of numbers like 93.184.216.34, right? We need a translator. DNS acts as the Internet's invisible phone book. It's this massive, hierarchical, distributed database that takes a human-readable domain name, like example.com, and instantly maps it to the numeric IP address the network actually needs to route your packets. When you type a URL, your query hops through this exact 3-step hierarchy in mere milliseconds. First, your resolver asks a root server, hey, who handles .coms? The root then points to the top-level domain, or TLD server. Second, your resolver asks that TLD server, okay, who handles example.com? The TLD server points to the final destination. Third, your resolver asks the authoritative name server for the exact IP address, and boom, you've got the numbers. Plus, the really cool part is that these results are cached locally at every single step, making future lookups practically instant. This quote from Paul Makapetris back in 1987 perfectly highlights that DNS is this unseen infrastructure making almost all internet services incredibly user-friendly. And it's not just for web browsing. As the document points out, it supports internet mail routing and general host address lookups too. Most people have absolutely no idea it even exists, yet literally every single web request you make depends entirely on it. Which brings us to Section 4, HTTP, the language of the web at the application layer. Okay, so once DNS hands us the IP address and TCP locks in that reliable connection, how does a browser actually ask for the web page? Well, HTTP operates right at the application layer, sitting securely on top of TCP. It is literally the language that defines how web clients, like your browser, and web servers format and transmit their messages. Your browser sends an HTTP request using a method like GET or POST, basically asking for a specific resource path. Then the server responds with a status code, like a cheerful 200 OK or that dreaded 404 not found, along with the actual content. And a key thing to remember, it's a stateless protocol. Every single request-response pair is a completely fresh start, independent of anything you asked for previously. Now, while newer versions like HTTP/2 and HTTP/3 have emerged recently to massively boost speed, with HTTP/3 even running over UDP to cut down latency, the core conversational semantics established way back when have remained wonderfully stable. This 1999 documentation of HTTP/1.1 shows how the whole foundation of requests, headers, and responses totally transformed the web. It allowed hypermedia access to resources from incredibly diverse applications, and it's still the bedrock of how we browse today. And finally, Section 5, the protocol stack in action, where we bring it all together. All right, here's the climax of our explainer. Let's combine all these isolated pieces into one cohesive picture and trace exactly what happens the millisecond you press enter on your keyboard. It's basically a beautifully choreographed 6-step dance that perfectly utilizes every single standard we've talked about. First, DNS resolves your human-readable hostname into an IP address. Second, TCP steps in with its 3-way handshake to guarantee a reliable connection to that IP. Third, a TLS, or Transport Layer Security Handshake, jumps in to encrypt and secure that channel. Fourth, HTTP uses that secure, reliable channel to get the web page. Fifth, IP routes every single packet back and forth based on those addresses. And sixth, the server successfully responds with your content. Boom, magic. The really major takeaway I want you to leave with today is the sheer genius of this layered design. Because each protocol relies only on the services directly below it, the internet is both incredibly universal and deeply extensible. Think about it. You can upgrade physical networks from old copper cables to 4G and then jump to 5G, or swap out HTTP/1 for HTTP/3 and do it completely seamlessly. You don't have to tear down and rebuild the entire internet architecture just to make an upgrade. It's future-proof by design. So I'm going to leave you with this puzzle to ponder as we wrap up. Based on everything we've just covered about the trade-offs between reliability and speed, if you were tasked with building a brand new real-time voice call application right now, which transport protocol are you picking? TCP or UDP? Really think about what happens to a live conversation if the data arrives late. Thanks so much for diving into the invisible rulebook of the internet with me. Catch you next time.